What's up, guys? This is Waleed, and today's problem is the reactor fuel and waste. So in the first question, what is the total thermal power generated by a reactor? So they want to find the total. Let's do red today. So the total multiplied times 0.3. 0.3 is the percentages. Okay, percentage that you're gonna have. It's gonna be equal to the 10 to the 3 to the third, which is this guy here. How much electric power the plant receives. So from this guy we get 3 times 10 to the 6 watt, which is the same as joules per second. Cool. For the second question, what is the rate of fission event in the reactor core? So this guy, you need to find the what's the energy released per fission. Okay, so in the video before I found that it was 179.6 million electron volt. The way you find this guy is you add these masses, so mass of the uranium, mass of the neutron, minus, you add those masses right here, and you find it from the table right below, above it. And then you multiply, once you find the mass, delta M, multiply it times 931.5 million electron volt, divided by C squared, U times C squared. And then you cancel those guys, and this one has a unit of the unit of the masses of this one per unit, and then you just find the answer, which is 179.6. If it's unclear, just go to the video before it. I might link it in the description below. So for this guy, I'm going to change it to joule per second. So the way we do that is we multiply it times 1.6 times 10 to the negative 19 joule, and this one electron volt, so we cancel electron volts, and then we get equal to 2.873 times 10 to the negative 17 joules. So we got it by joules. Now we need to just divide the, let me do it right there. So the number we find in the beginning times 10 to the 6, because this is joules per second, and then we divide it by 2.873 times 10 to the negative 17, and this is joules. So take out the joules out, and then we get a unit of 1 divided by second, so which is 1.159 times 10 to the 20, 1 divided by second. Cool. It's just unit manipulation. You don't even have to understand what we're doing, but just if you understand units, you can get the answers. So now, for number 3, what is the mass uranium-235 fission in 1 year? So let's change this guy to a year. So the answer we got, which is 1.159 times 10 to the 20 by second, and then multiply it by 60 second divided by minute, 60 minute divided by 1 hour, times 24 hour divided by day, 1 day, times 365 days divided by a year. So for this guy I got 3.65 5 e to the 27 by year. Okay. And now we just do this. So the total fissions multiply times the mass of the uranium, U-235. So this guy is going to be 3.65 e to the 27 year multiply times 235 atomic mass times 1.66 e to the negative 27 kilogram. Okay, now this is by unit. So we cancel those guys, and this one multiplied by a year because they want the whole thing by a year. But let's just get the whole thing, which is 1424 kilogram per year, and they want the amount per year, so multiply it by 1 year. Cancel, so we get 1424 kilograms. Okay, kilograms of U-235. So they told us that the fuel that's burned, it's only 2.9% of the mass is U-235, and the other percentages are 238, uranium-238. So they want to know the total. So the total times 0.029, the percentages, is going to be equal to the amount we got, which is 1424. Okay, so the total of the mass will be 1424 divided by 0.029, which is equal to 49106.89 kilograms. That's the total mass that we have. Okay. The second question, they're asking what's the volume of this mass. So we know that volume is equal to mass divided by density. So the mass is 49106.89 divided by the density, which is, if you press on the help button, they'll give to you just 19,000. I think it's kilograms per meter cubed, and this is kilograms. And the total is going to equal to 2.584 meter cubed. Alright, so for number 6, so it's a little bit tricky, but here you go, let's do it. So we need to change in the beginning the 2.5 times 10 to the 12th kilowatt H per year times, we need to change that, so 3.6 times 10 to the 6 joules divided by kWh. So each kWh is equal to 3.6 e to the 6th. Okay, and that will give us the answer in joules, which is 9 times 10 to the 18 joules per year. Okay, but that's how much the US use. But remember, there is efficiency, and that's only 30%. This ratio, this joules, this energy is just a ratio. So there is another 70% that's going to waste, because it's not as effective. The nuclear power plants are only 30% effective, as they told us in the question here. It's only 30%. So this is actually just the answer. This is just what the they give us, not how much they actually burn. So the waste is going to be way more. So let's find the how much is the total. Not how much is used, how much is the total. Okay, so total is times 0.3. This is how much is effective. It's going to be equal to 9 times 10 to the 18. Okay, and for this guy I got total. It's going to be equal to 3 times 10 to the 19 joule. Okay. So now let's also change the number we got in the first question, which is 3333.3 joules per second. Let's change that to a year, and then we just multiply it by 60 times 60 times 24 times 365. Okay, and that will give us 1.0511 e to the 17 joules. That's how much energy the one nuclear power gives. And then remember, its waste was, we got it in we got the volume of it in this question, in this answer, and the answer of number 5, which is 2.584 meter cube. Okay, so we just need to compare them together. So 3 times 10 to the 19 joules. How much waste does this one give? Okay, so multiply this by this, divided by this. So 2.584 times 3 times 10 to the 19 divided by 1.0511 times 10 to the 17. It's joule, so we cancel these meter cubed. And for this one I got 737.51. Cool. That's meter cubed. And for number 7, just write it on here. For number 7, if the waste were formed into a cube, what would be the length of the cube sides? So we have the cube. How much is this? The volume of it. So 737.51, and take the square cubic root of that, which will come up to around 9.034 meters. Cool. Alright guys, hope this helps. If you have any question, let me know. Good luck.